everybody. So today I'm going to start a new unit or a new chapter called moving charges and magnetism. That is, we are going to study the effect of moving charge or effect of magnetic effect due to current carrying conductor. Okay. So first I would like to do a brief introduction about this. So before I start introduction, we say that let's say 500 or the 600 or 1000 years back, the science, the physics divided into two parts. That is especially electricity and magnetism. So we say we have one branch of physics called electricities, another branch of physics called magnetisms. And people thought that these two branches or these two phenomena are unrelated to each other, right? So until in in 18th century or in year 1829, it was first discovered by Henry Christian Oz, right? So he was doing lecture demonstrations in the summer of 1829, and he was performing an experiment on current carrying conductors. And what he found was when a current passes through the wire, he found the deflection of magnetic compass, which is near current carrying conductor. So it was something like a new findings. Why? Because people never thought those times that current carrying conductor won't deflect a magnetic compass. To deflect a magnetic compass, we require magnetic field, we require magnets. All right. So this was found by Hans Christian Ost, right? So and then he started performing many experiments on these phenomena, right? And then what he found was that when you increase the direction or when you increase the current, the deflection is greater. All right. And when he reversed the direction of currents, the deflection is in the opposite directions. All right. So therefore this was found, right? So this is the currents coming out from this plate, and he found the magnetic compass. All right, magnetic compass around current wires start aligning in this patterns, right? These all are tangent, right? Magnetic compass are aligned tangent to the circular circle, right? Where the wire is passing through a centers, right? So when you reverse the direction of current, this is the current passing through, current penetrating through the surface, and the direction of magnetic compass is reverse. All right. So this was found by, and this is a new finding, right? And then moreover, if you just put iron filings around current carrying conductor, you see these patterns, right? A nice patterns or circular patterns. So this shows the magnetic field around current carrying conductors. All right. So one more. So this and this was found by and this was a new finding, and then from that onwards, the physicists came to know that yes, there is a link between the current carrying conductor and magnetic field and magnetisms, right? So that means that current carrying conductors, the current produce magnetic fields. Normally we feel that it is the magnet which could produce a magnetic field. Now it is current which is electricity which could able to produce a magnetic field, right? So this is the first found by Hans Christian Ost and in year 1829. All right. So this is what we have now. Now in this chapter, what we are going to study is now if if a current carrying conductor could produce a magnetic field, then if I keep a current carrying conductor in a magnetic field, and it will exert electric force. So force on a current carrying conductor in a magnetic fields, a moving charge, when I let a charge to move in a magnetic fields, then moving charge also experience a magnetic force. And then what we are going to study, right? Studies the magnetic field produced by current carrying conductors. All right, and then we will studies if I have a two wire carrying a current, these two wires exert force on each other like two churches. If I have two churches start exerting force on each other. Likewise. So this all what we are going to study in this chapter. All right. So now the first what I'm going to do is, this was the Lorentz force. Lorentz force. So what I'm going to do is let me do a small recapitulation of electrostatic, right? So if I have a charge, let's say charge Q at positions R, all right, and if I have a charge small q, let's say small q at position R with respect to charge Q, I say this is at origins, all right. So therefore, electric force on a small q would be equal to 1 by 4 pi epsilon naught q divided by r square. This is electrostatic force. This is the electrostatic force. Electrostatic force experienced by q due to capital Q. This is what we call as electrostatic force. And we have also studied that at position vector r. At a position vector r, electric field at r would be equal to q divided by 4 pi epsilon naught r square. So therefore we found these relations. This is small recapitulations. All right, this is what we have. This is for electrostatic, right? This is for electrostatics. Now what I'm going to do is if I have a charge moving in an electric field and magnetic field. Now if I have a charge Q moving in a magnetic fields, moving in electric field E and magnetic field B with velocities, let's say with velocity V, then I say that this moving charge experience both electric force as well as magnetic force. So this total force experienced by a moving charge would be Q. This is electric field, and then V cross B, this is magnetic force. So this equation implies that if velocity is 0, let's say if velocity is 0, then this is simply electric force. So if a charge is at rest, then charge experience only electric force. If charge is moving, then charge experience electric force as well as magnetic force. So therefore, this is equal to plus Q V cross B. All right, and this can be written as electric force plus magnetic force. This is what I have. So what is the magnetic force? All right, this is what we call as the Lorentz force. This is what we call as Lorentz force. This is what we call as a Lorentz force. This is what we call. Now we would like to stress more on this because we have already studied this, right? So now I would like to do this. Now I would like to do more discussion on magnetic force. So this magnetic force, all right, would be equal to QV. This is the magnetic force. This is the magnetic force. All right, and as far as electric force is concerned, direction is along electric fields. Direction is along. Alright. What about magnetic force? The direction is magnetic force. Direction would be is perpendicular to the plane containing V and B, and the direction is given by what we call as right hand thumb rule. Right hand thumb rule. Direction is given by what we call as right hand thumb rule. This is what I have, right? So I would like to tell you how direction can be found. So look at here. Direction is given by this, and the magnitude is, look at here, magnitude is equal to sine theta, where theta is angle between velocity and magnetic fields. Theta is angle between velocity and magnetic fields. Alright. Now how to find out directions? Look at here. This is how the direction is found. This is magnetic field. Alright, this is the velocities, and right hand thumb rule says that it has to go like this, right? Look at here, I say this is the magnetic field, this is the velocities. You have to do like this is the angle between magnetic field, and this is the magnetic field, this is the velocities, and you have to go like this. You have said this cross product in class 11. I'm going to do this. Velocity, this is the velocity, look at here, this is the velocity, and then velocity goes to what? Magnetic field. Go from velocity to magnetic field. Velocity to magnetic field. What is the direction of magnetic field? Force. Force is this, right? Here in this case, this is a plane, and this is the direction of velocity, and this is the direction of magnetic field. And then what about the direction of force? Like this. All right. Force is this. So direction of force is given by right hand thumb rule. And how you have to do is first do like this. And you have to go from velocity to magnetic field. Go from velocity to magnetic field. So this is the plane. This is plane something like this. This is the plane. Here we have a velocity. Here you have a magnetic field. And then magnetic field, velocity to magnetic field. Velocity to magnetic field. Then force would be upward. Force would be upward. Alright. So if it is just the opposite, I have a plane like this, I'll just do the opposite, right? If I have a plane like this, if this is the velocity and this is the magnetic field, then it will go downward. It will go downward. The force is going to be downward. This is the magnetic field. It is something like this. If I have a plane like this is the velocity, this is the magnetic field, velocity, magnetic field, then goes like this, curl like this, curl like this. You have to curl from velocity to magnetic field. Curl from velocity to magnetic field. Then the direction of force is downward. It is just the opposite. If I have velocity like this and the magnetic field like this goes from velocity to magnetic field, it is upward. So this is what I have shown you here, right? And then this is again what I have for positive. Look at here. This is the magnetic field. This is the velocity, and then magnetic field. Magnetic field is this, right? So velocity, magnetic field. Look at here. Velocity, magnetic field. Velocity, magnetic field. Where is the direction of force? Force is in these directions. Force is in this direction, right? And in case of negative charge, this is just the opposite of positive charge. So negative charge, velocity is upward, and this has to be opposite to. So if a positive charge is in this direction, negative charge has to be in these directions. If a positive charge is in this direction, negative charge has to be in that. One positive charge and negatives are opposite, right? So that you should keep in mind. Very, very important, right? Again, I am repeating. This fingers, right? Are the direction of velocity, and velocity goes toward magnetic field. Velocity goes toward magnetic field. Then force is going to be this. This is the force. All right. So this is what we have, right? So now, So now let's do a small discussion on this. This tells that now if V is along B, if V is along B, then theta would be equal to 0. So therefore, force is going to be 0. That is, there is no force. If a velocity is, if a charge is moving along a magnetic field, then the charge does not experience any force. Charge does not experience any force, right? And now if V is perpendicular to B, where theta is equal to 90 degree, then so this is then force is equal to QVB. This is maximum force. This is the maximum force. Maximum force. This is going to be a maximum force. Maximum force. Now, if I say if theta having some angle theta, then force would be equal to QVB sin theta. So these are the conditions. So therefore, what you have to conclude and infer from this expression is that no force is going to be experienced by a moving charge if charge is moving along electric field. Charge is moving along magnetic fields. Charge will experience a maximum magnetic fields if velocity is perpendicular. Velocity of a charge particle is perpendicular to magnetic field. This is what we have. This is what we have. All right. So this is what we have. This is what we talk about a Lorentz force. All right. Now what I'm going to do is I'm going to extend this discussion to our current carrying conductors. When I say there is a current in a wire, we would visualize that the charges are moving in our conductor. And the moving charge, the rate of moving charge in a conductor is what we term as a current. All right. So therefore, this is what I have, right? So magnetic force on a current carrying conductors. Magnetic force on a current carrying conductors. All right. So let's say I have a conductor. Small n is a number density. Number density is nothing but number of free charge carrier per unit volumes, and then I have A is area of cross sections. A is area of cross sections. L is the length of wire. And Q is the charge of each charge carrier. Then V is the velocity. V is a dip velocity. When we talk about a current, the average velocity we are going to see is a dip velocity. Right here, dip velocity. Dip velocity. All right. So now we will have these equations. So the magnetic force would be equal to QV plus B. All right, Q is total charge. I'm going to say there's something like this. Total charge. All right. So total charge is going to be number density into volume. Number density into volume is going to be total number of charge carrier. Number density into volume is the total number of charge carrier, and this is the Q is a charge of each charge carrier, and V I am going to refer is a dip velocity, right? Dip velocities. D I am going to refer as a dip velocity. All right. So therefore, my expressions is equal to NALQ VB cross B. Alright, this is what I have. Now I would like to introduce one more term. This we have done lower class just now last time. This is a current density, right? Current density is what we refer as NQVDL is what we call as current density, right? This is what we call as a current density. Alright. What is current density? Current density is equal to I divided by area. Alright. So this is a dip velocity. Dip velocity is going to be, let's say it is moving along my x-axis. dx is divided by dt. Alright. And dx, and then since this is a current density, this is going to be something like this. Since this is the current density, this denominator will be having area. Alright, so area get cancelled out. Alright, so this is what we have, right? I'll do this. And number density, right? Number density is equal to area, and then distance travel is x. Alright, then this is going to be a q, this is going to be a dt, and then this is current, right? And divided by area. This is how I obtain, right? So area can cancel out. So therefore this is equal to Vd. Alright, this is how we obtain. This is how we obtain. Alright. So having this, now I just write this. This is current density. Current density is equal to, I'll do like these equations. AL cross B. So this is going to be our current density. JAL, and then cross B. J is a vector quantity, and then this B is going to be JL is equal to I, right? JL is I. Once I put I, the length become. Alright, so this is what I have, right? So therefore I just write magnetic force on a current carrying conductor would be IL cross B. This is magnetic force on a current carrying conductors. This is magnetic force on a current carrying conductor. I'm sorry, I have to put here a vector sign. Again, the direction of a force is perpendicular to the plane. Perpendicular plane formed by L and B. So this is what I have. Right? So I'll give you one example here. Look at here. I would like to introduce one sign convention. This is a sign which indicates that it is coming out of plane. This is what we call as out of plane. Right here. This is what we call as out of plane. Out of plane. Direction is out of plane. This is dot. Dot represents that it is coming out of planes. And this is cross. Cross represents into the planes. Into the plane. Alright. Current is into the plane. Charge move into the plane. Whatever. Right. So this is what I have. So look at here. I have a magnetic field something like this. I have a magnetic field something like this. Now this is the current wire. Direction of current is this. Now we have to find out the direction of magnetic force. So what is the direction of magnetic force? Again, this is given by right and thumb rules. L cross B. Alright, the direction of L, right here, right? Direction of L is along currents. Direction of L is along current. Direction of L is along currents. And this is sometimes we call as a length elements if I choose a small portion of length, right? So L cross B. Look at here. L cross B. B is into the plane. This is B. This is a B and this is I and L. All right. So L cross B. So direction of force is this. This is the direction of force. Again, I'm showing you L cross B. This is force. Now, if I have, suppose, if I have current, suppose I have a wire and whose current is in that directions, then I will say this is a length directions and curl into the plane, and the direction of force is going to be. This is how the force are done, right? And then again, I would like to do a few cases. So first, magnitude of force can be represented by IL B sin theta. Theta is angle between L and B, right? And I say if I choose a small elements, all right, then D we would like to represent by this. All right, this is represented by DL cross B, and DL represents the length elements. Length element means small portion of length. Length element refers to a small portion of length. Alright, so this is what I have. Alright, so total magnetic force can be found by summation, right? So I just sum up all the length element, all DL cross B. So this is what I have. Alright, now I would like to do a small cases, right? A few cases. What about maximum force? What about zero force? Like that. So if theta is equal to let's say 0 degree, that means DL is along B, then equal to DL B sin 0. Sin 0 is 0. So force is going to be 0. Alright. Force is going to be 0. 0. Now if theta is equal to 90 degree, then DL is perpendicular to B. So therefore I equal to DL B sin 90 degree DL B. So this is what this is the maximum force. This is the maximum force. So this you should keep in mind. Alright, this is the maximum force. Zero force, I just say maximum force. Maximum force. Alright, so I have given you an example here. Direction examples I have given here. So this talks about magnetic force on a current carrying conductors. Current carrying conductors. Alright, now we would like to study the path of a moving charge in a magnetic field. Path of a moving charge in a magnetic field. This is the path of a moving charge in a magnetic field. So we have learned in class 11 that if the force is along a direction of displacement, then we would do some work. Alright. If I say if the direction of a force and the direction of displacements are perpendicular to each other, then we would say that you won't get any work. Work done is always zero. Work done is always zero, right? And then one more concept we have studied, that if I let a particles or the object to move such that the direction of velocity and the direction of force are perpendicular, right? If a direction of a velocity and the directions of force are perpendicular, and we would say that the path of such a particle would be circular path. This is the velocity, this is the force, and the path would be, this is done in class 11, right? This path would be circular path, and this force is what we call as centripetal force, right? Force is what we call as centripetal force. This is done in class 11, right? Very detailed class 11, right? So this is what I'm going to do here, right? And this is what exactly Earth goes around Sun. This is exactly Moon goes around Earth. All right. So here, what I'm going to do is, I have a charge. I have a positive charge moving in a magnetic field like this. I have a positive charge moving in a magnetic field like this. So let's say I have a positive charge. I have a positive charge. This is the magnetic field. This is the magnetic field. This is the magnetic field into the plane. And I have a positive charge like this. This is a positive charge moving in these directions. This is, and where is the direction of force? Force would be downward. Force is downward. Force is downward. And that means this charge particle goes around a circular path. Charge particle goes around a circular path. So the path would be like this. When the charge particle reach here, by the time direction of force is like this, direction of velocity is this, this is velocity is this, and there would be a force. Force is this. Alright? And it goes like this. When it reach here, direction of velocity is this, and the direction of force would be up. Look at here, direction of force is up. And goes like this. And when it reach here, direction of velocity is this, force, and this is how we get it. So that means this undergo a circular path. This undergo a circular path. So path is going to be a circular, right? Path is circular. Circular with, let's say, with the radius r. Let's say with radius r. With the radius r. So look at here. So having this, I just say that I have a charge particle Q moving with velocity, velocity v in and uniform magnetic field, in a uniform magnetic field, be shown here. Alright, now it undergo a circular path. Right? When it undergo a circular path, that means it has a centripetal force, right? So what is the centripetal force? It has a centripetal force, and centripetal force is going to be, this is the centripetal force, and normally centripetal force is given by this. And V square by M is a mass of charge particle, V is the linear velocity of a charge particle, R is a radius. So since I have chosen a radius as a capital R, I am going to see this is R. And who provides this centripetal force? When Earth goes around Sun, how Earth could go around the Sun? That means Sun provides gravitational force of a Sun provides a necessary centripetal force. Likewise here, who provides centripetal force? Alright, then I would say that this is the magnetic force. Magnetic force is going to be Q, V plus V. Alright, and this is equal to QB B sine theta. So theta is 90 degree. Why? Because look at here. Alright, velocity and magnetic fields are 90 degree. So therefore, this is equal to VB. This is the centripetal. This is the magnetic force, and centripetal force. The magnetic force provides centripetal force. This is the centripetal force. Therefore, I would like to write here this is equal to magnetic field, and then which is equal to m square v square r. Let me write VB, and these two cancel out. Finally, we get NV R equal to QB. How much is R? R is equal to QB divided by NV. Alright. This is the radius. This is the radius. So whenever we talk about the path of a circular path, whenever we talk about circular path, a circular path is defined by what we call as a radius. Right? If a radius is big, circle is big. If a radius is small, then path is going to be a small. Right? So this is what I very, very important equations. Very, very important equation. R, right? Radius. And then velocity would be, and I say velocity would be V is equal to Q B divided by MR. This is the velocity, right? Velocity would be this, right? Radius, alright, and velocity would be this, right? Look at here. Right. This is the velocity. Now, let me go a little further, right? So, if I have a velocity, let's say time. What do you mean by time period, right? Time period is time required to complete one circle, one round, right? So this is what I have. This is the velocity, right? So now I substitute the velocity. What is the velocity? QB. All right. QB divided by MR. R cancel out. 2 by M divided by QB. So this is the time period. 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 Alright. If it is time period, then frequency would be equal. Linear frequency would be equal to what? 1 by time periods. So therefore linear frequency is equal to QB divided by 2 by M. This is the linear frequency. This is the linear frequency. This is the velocity. This is the velocity. This is the linear frequency. This is the time period. Now what about angular frequency? What about angular frequency? Angular frequency would be equal to 2 pi frequency. So therefore angular frequency would be equal to, this is angular frequency. This is angular frequency. Now look at this, right? Look at the radius. Now this is the nice the finding here, right? When you look at the radius of path, the radius of a path is inverse to velocity. The radius of a path is inverse to velocity. That means if a velocity increases, and the radius is going to increase. If a velocity increases, the radius is going to increase. If it's so, then what we found is the time periods is independent of the radius and the velocities. It is not that if a velocity increases, time period is going to decrease. It's not something why, because the radius of a path is inverse to velocity. So therefore, because of these factors, the time period is independent of velocity and radius. So therefore, time period is independent of radius and velocity, right? So therefore frequency is also independent, right? Whether a charge is moving very fast or a charge is moving very slow, the frequency would remain. Why? Because if a charge is moving slow, then the path would be a smaller. If a charge is moving very high, the path would be greater circle, right? So this concept helps the scientists or physicists to design what we call as a cyclotrons, right? So the foundations or the basic understanding about cyclotron is based on these principles. That means the radius and velocities are inverse, so the time period doesn't make any difference. Time period is independent of these two. So this is very, very important, right? So I'll show you these diagrams. This is what I have. This is the diagram, right? It is circular path. It is a circular path. All right. So the diagram I have written here, same diagram actually I have written, right? This is a radius. I have written a radius is a big R, so it doesn't make any difference. So the force are always into the towards the center. This is what we centripetal force means, force that is going towards the center, right? Because of which you have charge moving along a circular path. Charge moving along a circular path. Charge moving along a circular path. All right. Now, this is the case where V and B are perpendicular. This is the case where V and B are perpendicular to each other. Perpendicular to each other. Perpendicular to each other. This is the case where V and B are perpendicular. Now, let's say if V and B are not perpendicular, with having some angle, right? If V and B are having some angles, if V and B has some angles, let's say theta, then what about the path? Then what about the path? What about the path? If V and B having some angle theta, then what about the path? This is what we are going to study, right? So look at here, I'll do this small. Same I'll do here. Alright. So this is the magnetic field. This is the magnetic field, and this is z-axis, x-axis, or y-axis. Alright, now velocity goes like this. This is the velocity. If a velocity goes like this, it has two components. One is along magnetic field. So this velocity, this velocity which is along has no magnetic effects. Has no magnetic effect. No magnetic effects. What about this? Alright, this is what we say that this is perpendicular to magnetic field. So therefore this is the force. Where is the directional force? Force goes like, if force goes like this, if a force is going like this, then it has to circle like this. If force is like this, circular has to be this. If force is like that, circular is why? Because this is the centripetal force. Now here in this, again I am repeating, force is in these directions. So therefore this goes in a circular path. So this is the circular path like this. This is a circular path like this. And why it is moving along this? Because of horizontal velocity, because of horizontal components. So horizontal component has no effect, no magnetic effect, so it goes along like this, and then this is the perpendicular component of a velocity which makes the charge to go along a circular path. So therefore, you have a two component of velocity. One makes a charge to go along a circular path, another make a charge to move along horizontal. So what would be path? Path is what we call as a helical path or helical motions. Helical path. So helical is the two simultaneous velocities. One is a perpendicular velocity, another one is a horizontal velocity. So therefore, this all together I say it goes helical path. This was helical path. Now I would like to define what is pitch. Pitch is equal to distance moved in a one time period, right? Distance moved by one time period, right? So distance moved by one time period, velocity into by time period. This is the pitch, right? So therefore, this is the horizontal velocity, and therefore this is equal to 2 pi time period is going to be this. I'm sorry, this is going to be time period. Time period is going to be this, right? 2 pi m divided by QB multiplied by this is the pitch. Alright, this is the pitch. So pitch is the distance moved by a charged particle in a one time period, in a one round. So this is what I have called a helical motion. So you should keep in mind, if charge has only one component of magnetic velocity, which is perpendicular to magnetic field, it goes around the circular path. If I say if a velocity is along a magnetic field, then it doesn't experience any force. Now I have a charged particle which has both along as well as perpendicular, then it goes helical path. Alright, circular as well as goes along horizontal. Alright, so with this I will stop here.